Hi, welcome to Computing Foundations. This is a YouTube channel for beginners who want to learn about programming, computers, and the math, science, and art behind this world-changing field. I'm Josh Kilpatrick, a retired software engineer. I want to take a second to thank you for watching the channel, and if you will, please subscribe, like, and share your comments to help me improve my work. Today we're continuing our journey learning the C programming language. We just have a few more videos left in this series, and we've reached an important topic called dynamic memory allocation. So let's jump in first by understanding a little bit about the kind of memory we've already seen up until this point. So in an example program like we've seen up until now, you might have had a main function in which you declared various variables and initialized them to have values, or maybe you didn't initialize them. These kinds of variable declarations are referred to as static memory. What we mean by that is, as we're writing the program itself declares a certain amount of memory that is going to be needed when the program is loaded into memory. So what actually happens, I've shown you a diagram here on the side, that when you run your program, what gets loaded into the computer's memory is, first, at the highest address, we kind of load the program in reverse, in memory, if you will. At the highest address allocated to the program, we load in the actual zeros and ones that represent the instructions of the program. This is a computer assembly, well, it's not assembly, but it's computer binary code that the computer, your processor, knows how to interpret. So your actual program with all of its instructions and statements gets laid out into memory. Next, there's a section of memory that gets dedicated to all the variables that you've declared in your program. All of your constants, that are outside the main function, plus everything that you've defined inside the main function, and in any of your libraries gets allocated and placed into memory. So we call this static memory because as soon as the program loads, all of this memory gets allocated and it's ready to be used by the program. Well, also in the program memory space, there are two other areas of memory besides this program and the data area. There's what is called the heap and the stack. The stack is an area of memory that grows from a very low address and it grows to higher addresses. And the purpose of the stack is that every time your program calls into a new function, memory gets allocated in the stack grows down. Memory gets allocated to hold the variables and parameters that are used by the function. If I call one function, and then within that function, I call another function, and then within that function, I call another function, this stack area of memory keeps growing. And what is allocated on the stack are space for the variables that will only exist inside the scope of the function. This is called the stack memory, and it's a kind of dynamic memory that's automatically handled by the computer for you as your program calls into the different subroutines and functions that you've defined. Well, another area of memory that grows from large addresses upward toward smaller addresses is called the heap. The heap is an area of memory that can be utilized and reserved by the running program. And as programmers, we're allowed to write statements into our program that will reserve and utilize areas of the heap. And that's what we're going to learn about today. It's how a programmer can make use of dynamic memory that we don't have to declare ahead of time. So let's think a little bit about why we would want dynamic memory. So what happens if I don't know ahead of time as I'm writing my program how big I need my array to be or how much data I'm going to have to process? What if, remember the example of the phone book application that we wrote as an exercise, what if my phone book starts to grow beyond 100 entries, but I only allocated space for an array of 100 entries? How would I grow the amount of space that the program is using so I could continue accepting more and more entries in my phone book? Well, the truth is we haven't seen how to do this yet. We've only seen how to allocate things statically, where you have to know ahead of time how much memory you're going to need. What if, remember the example where we wrote a scoreboard for 2 teams that were playing 6 games? Well, what if I don't know how many teams I need to keep score for until the program is running? And what if they need to play more than 6 games? What if I don't know how many games they need to play? How would I write a program that could grow the amount of memory space it's using based on what's happening after the program starts running? So dynamic memory is about things that are unknown until the program is running. A little aside here that I want to clarify. I drew a picture, but I didn't talk about it yet. Every program that gets loaded into the computer, every program that you run, gets a little area of memory that's reserved just for that program. And in theory, the memory where these programs are loaded, they don't interfere with each other. So any given program, like this program, will get loaded into a slot of memory where the code that describes the instructions of the program is written into memory, the static variables are written into memory, and then a certain amount of space is reserved for a stack and a heap. As programmers, we can kind of think of the stack and the heap as being infinite, but in reality, they're not. The operating system has allocated a set amount of space for the program, and if you exceed that amount of space, your program will be terminated by the operating system. So every program gets laid into memory in separate areas of memory, and when we switch from one program to another program, the computer just reloads what it's working on based on a different area of memory that represents a different program. Okay, so dynamic memory is pretty simple. We use a function that is defined in the standard library, stdlib, standard library.h. The function is called malloc, or malloc, memory allocation. The function returns a void pointer, which I'll describe and talk about in a minute, and it receives as input an unsigned integer, which represents a number of bytes that you want to reserve on the heap. What is this void star pointer? We haven't talked a lot about this yet, but C defines a type called void, which means this is a generic type, an unknown type. And a void pointer is basically an address to an area of memory where we have not yet declared what this area of memory is going to be. So we're not declaring that we're going to use it as integers or a structure or a character. We're just saying, I want a pointer to an area of memory, and I'm not making any statements. I'm not making any assumptions about what will be in that area of memory. This is the purpose of a void pointer. So how do I call malloc? It ends up looking something like this. I declare a variable of a pointer type. Usually, I'm going to be specific about what I'm planning to store in this memory. So here, I declare an int star called my mem. This is an integer pointer. and I assign to it whatever gets returned from malloc 24. Remember, an integer is 4 bytes. So if I ask the malloc routine to give me 24 bytes, I'm asking for enough space to hold 6 integers. So after this function executes, I have a pointer that's pointing to a space of memory that could hold 6 integers consecutively. Here's kind of a quick sneak peek of what it might look like. So this mymem variable is a pointer. It's an area of memory of 8 bytes that holds an address. Here I've assumed the address is 08, and that address is an area of memory starting at 08 and representing 24 bytes of reserved space on the heap. So here I have my variable. It is a pointer, it holds an address, and the address refers to an area of memory that is 24 bytes. So this is how I dynamically create an area of memory. Well, another thing that's important to understand is that if you are going to dynamically create memory in your program, you need to make sure that when you're finished using that variable, when you're finished working with that variable, you release and deallocate that memory. Because again, the amount of memory available for your program isn't infinite. You don't want to keep using more and more and more and more memory infinitely, because eventually you will exhaust your heap and your program will be shut down. So a well-running program utilizes a constant amount of memory or a growing and shrinking amount of memory such that it never exceeds the maximum heap size. So how do I release memory that I've dynamically allocated? There's another method that we can use in standard library called free. Free doesn't return anything, it's a void function, but it receives a void pointer to anything, and as long as that void pointer is pointing to memory that has been allocated dynamically by the malloc function, the free function will release it back into the heap, telling the program manager, hey, the programmer no longer needs this memory, you can put it back on the heap, and if later somebody calls malloc again, you can re-give this out. Nobody's using it anymore. So this is called freed memory. So a quick example here, I define a variable called myMemory, which is a pointer, integer pointer, that will point to an allocated area of 24 bytes. Then later in my code, I can simply call free mymem. This integer star pointer will get downcasted into a void star pointer automatically. You don't have to manually cast it. And the running program, the memory manager, will free that memory. Now, the size of operator becomes very important when we're using malloc, because we don't want to assume and write into our program what is the size of an integer or what is the size of some other aspect, some other float or a character. We want to just ask the compiler, we want to ask the program manager, how much memory do I need to store this variable? And size of is the operator that lets us do that. So a more correct way to declare an integer pointer to an array of integers, this is just an area of memory that has enough space to hold multiple integers, is to call malloc and then say, okay, I want my array to hold 6, what? 6 size of int. Now on my computer, size of int will return 4 because an integer is stored in 4 bytes. That's common in most modern computers, but your computer could be different. So the size of operator will return how many bytes are needed to store this type, and then we multiply it by 6 so that now malloc will give us enough space to hold 6 integers in memory. Once I've done this, this pointer that I've declared can be used much like an array. What happens is the compiler is going to convert this bracket syntax into pointer arithmetic on our behalf. So if I want to get the first integer in this area of memory, I just say darray 0. I could also just say dereference darray and set it to a value. That's dereferencing the pointer so that I'm getting the first integer that's being pointed to. Excuse me. I could have also added 1 to darray and dereferenced it. This would have given me access to the second integer in the array. Just let me write that here so it's clear. So if I want to access darray 1, that is the second element in the array, I could also say dereference the darray pointer plus 1. And what would happen is 4 bytes would get added to the address of darray. Why 4 bytes? Well, because I've declared darray as an integer pointer, and integers take up 4 bytes. So when I increase the address 4 bytes, I'm moving to the next integer in the block of memory. Okay, so we've talked a little bit about allocating memory, and mostly the examples I've given you so far have been arrays. Let's just talk a little more specifically, though, about arrays. So we've already seen how to create a one-dimensional array. I just say char star or integer star. I give a name to my variable, and then I allocate a number of units of memory that are of the size of that type. But what if I want to create a 2D array? Well, this gets a little complicated. We need to declare a variable that is referred to as a double pointer or a pointer to a pointer. Here I declare a pointer to a pointer called name, and I run a malloc for 100 units that are the size of a character star. So what I'm saying is this variable is an array of 100 pointers to, or an array of, it's an array of 100 character star pointers. So the name variable is a pointer to an array, which is an array of 100 pointers. This is how we declare a two-dimensional array using dynamic allocation. So, helping you visualize this a little bit, this 2D array is going to be an array of 0 to 99 pointers. Each pointer will be set up to point to another pointer, which is the beginning of an array. So the way I do this now is I'm going to visit each element of this first array, of the name array, and I'm going to allocate again a space for 20, not character stars, but characters now. So I've allocated space for 100 pointers. The pointers point to space, or a pointer to space, that is big enough to hold 20 characters. So in the end, I'm going to end up with a bunch of pointers in memory that are pointing to other areas of memory. And this is how I allocate a two-dimensional array. Once I'm finished, I can access a particular item in one of these arrays by using name sub1 sub3. So here I'm pointing to the third, or I'm referencing the third character in the second array. So I'm getting the pointer to the second array of characters, and then I'm asking the compiler to bring me to the third element. So 1, 2, 3, the third element of my array. So this is basically a quick overview of how to define one-dimensional and two-dimensional arrays. A three-dimensional array would have the same strategy, but it would be a pointer to a pointer to a pointer. So it would be a char star 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 array. This is a little complicated to make sense of. In this video's program, which is called Program 15 Dynamic Memory, I walk you through the process of allocating dynamic memory for various types of variables, including a structure, a one-dimensional array, and a two-dimensional array. And I show you a couple different ways to handle two-dimensional arrays. You have a couple options of how you can define them. And if you just study through this program, I think it will make more sense to you than I could probably do by waving my hands here. All right. In order to really help us get our head around this and to feel really comfortable with these dynamic memories, I want to offer you another programming challenge. So what I want you to do is write a program that after it starts will receive from the user, from standard input, from the keyboard, as many sentences, characters, words as the user wants to type in. So as the user is typing in these words and sentences, you'll read them into a string of 50 characters that you've allocated as the program started up. But if the user happens to type more than 50 characters and you've run out of space in your character buffer, what I want you to do is allocate a new character buffer that's twice the size of your current buffer, so 100 characters. Copy the original 50 characters into the 100 character buffer and keep going, keep reading from the user. And as the user exceeds the size of your buffer, just continue on and on and on, expanding your memory to hold this larger area that the user's typing in. Finally, when the user types a Q for quit on a single line and hits enter, I want you to detect that the user has entered quit. So they're done entering things in. And then I want you to print out a couple statistics. I want you to print out how large is the string, how many characters are taken up by the string that the user ultimately entered in, how much space, I'm going to make this a dot 1, how much space are you currently allocated? How big is your current buffer? How many words did the user enter? So I want you to count spaces. How many spaces? And then as long as there's data between the spaces, those are the words. So how many words did the user enter? And then finally, print out to the screen the entire paragraph that was entered by the user. So we'll echo out the statistics and then dump the paragraph, and then the program will exit. So in order to make this work correctly, you'll have to allocate dynamic memory as the user keeps typing. You can reduce the original size of memory down to just 10 characters if you want to practice faster. You don't have to type as much. You just want to exceed the current buffer and jump to the next buffer. So be careful with your null characters that mark the ends of strings, because remember, if the user has typed past the end of your buffer, the fgetS function will not store the new line into the array that it's reading. So you need to be prepared for that and make sure that when you're copying from one array into your larger array, you're aware that your array may not be null terminated. So you need to be very specific when you use string copy so that you copy just the amount of space that you mean to copy. So good luck with the programming challenge. I'll post a video later with the solution, and I hope this gives you some good practice with dynamic memory, a topic that will become very important as we begin our next series of videos on data structures, where allocating dynamic memory is a very common technique to grow and shrink the amount of space being used by your program. Good luck, and we'll see you in the next video.